Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Good day, everyone. It probably feels to you like a whole lot of things are happening at once, and I guess that's because they are. It's the last week of the first half of semester. We've got an exam tomorrow. I hope everyone knows that. We've looked up the exam timetable. Is it in the afternoon? I think it is, but double check the timetable. I'm not the official source of this information, but yeah, it is on tomorrow. That is redeemable if for some reason you can't do it, or indeed if you get a poor mark, it doesn't matter in the sense that the larger percentage of your final or your midterm is the percentage that will count for your midterm, 20%. So that's what redeemable means. But nevertheless, it's a good chance to practice doing things under exam conditions. You have 90 minutes, and there'll be a few questions, and we've done, as has been said many times, no continuous random variables covered on that. So it's very similar to the stuff we talked about on the assignment and the quiz. So definitely probabilities, methods of calculating those, bit of combinatorics, bit of discrete random variables, expectations, different methods of finding expectations and probabilities, and maybe we'll talk a little bit more about that later in this class. And so that's all happening at once. We also have the assignment due tomorrow. I hope everyone knows that's due tomorrow, so hand it in before you do your exam. Hand it in person, please, if you could. Email me if you can't, but otherwise please do hand it in person. Not to my office necessarily. The official thing says go to level 4 of the CBE building, so that's what they have, an office staff there until 5 p.m. So, but tomorrow you'll have to get it in before 3 p.m. because that's the deadline, otherwise you would be marked late. So that's all mechanics. Now, we also have a lot going on in the lectures so far. We've pretty much, it'll surprise you, but we've pretty much finished the chapter that is on continuous random variables, and that's because there wasn't a whole lot in that chapter. We talked about what a density is, we talked about what, cumulative distribution functions, so PDF and CDF, and we talked about how to calculate expectations. And then we did a few examples. Now I've got probably one more example to give you of these prominent continuous random variables, and the rest will be on the tutorial this week, a bit more talk about the gamma, and that's it. And then but it's not like we're finished with continuous random variables, because the next chapter is multivariate distributions, which includes continuous multivariate distributions. So I'll be seeing a lot more of discrete and continuous random variables the whole course, but that's the end of the chapter once I've done one or two more random variables. So let me do that now. I want to talk about the beta random variable, and a reminder about the gamma. Okay. Now, a lot of this, will be elaborated on the tutorial this week. But I just want to give you. This is what you can take to be the definition of this gamma random variable. It is, of course, the key thing is x to the power a minus 1. It's an always positive or non-negative random variable because it doesn't matter whether you include 0 or not, it's continuous. But x greater than 0, x to the a minus 1, e to the minus x divided by b. Now, the denominator is b to the a gamma of a. Now, in terms of what is gamma of a, it's exactly the thing that's needed to make that a density. And as we know, densities must integrate to 1. So gamma of a, if you just imagine b being equal to 1, then gamma of a is the integral from 0 to infinity x to the minus, a minus 1 e to the minus x dx. So that's the definition of it. This makes sense for any a greater than 0. And I should say that's quite an important stipulation for the gamma. Both its parameters should be positive parameters for that to be a non-degenerate gamma distribution. So this makes sense. If you're wondering why a greater than 0, it's because if you have x to the power minus 1, then the asymptote at 0 is just a little bit too steep to integrate. If a is a little bit greater than 0, then it's like x to the minus 0.9 or so. That's a finite integral. Anyway, it doesn't matter. This is never infinity, this integral. It's a famous thing, and you can even have a formula so important that I'll even write it, a minus 1 gamma of a minus 1. And so that actually means that for integers you get factorials. Gamma of a is a minus 1 factorial for positive integers. There's also a formula that you'll find on the tutorial involving half integers. It's got a root pi in it. So all these things are connected. And also a fact that we found was that, now you might wonder, why is this gamma work for every b? Well, you have to use a scaling property. I'll say that b is called the scale parameter. So the scale parameter is nothing other than talking about how big it should be. And this is the shape parameter. Okay? So a substantially changes what it looks like. B doesn't change it at all, it just makes it bigger. So b times a gamma a1 is a gamma ab. Now, the other thing that we have is that, we'll talk about this later. We had normal, of course. If I have multiple normals, we'll talk about this more in the multivariate distribution case, but if I have d normals, if they're all IID, normal with mean 0 and variance 1, the fact is that, well, certainly z1 squared has the distribution chi squared with 1 degree of freedom, 1 meaning that I've squared one random variable, one normal, and the definition of that's exactly the same as gamma happens to be parameters 1, half, and 2, and we pretty much did that. We derived what the density of chi squared 1 was. It had an 1 over root x, e to the minus x over 2, and that pretty much was a conclusive case that it had to be this because the constant is determined. It's also a fact that we'll talk about probably just in a moment. It will, since I've brought that in, another fact is where these are independent normals, it's quite important that they be independent. If, for instance, they were all the same normal, if you just had d copies of the same variable, then by adding all the z1 squared plus z2 squared plus dot 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 plus zd squared, if you assumed, contrary to what I said, that they're actually all just the same variable, then you would just be multiplying by d, so the scaling would go up by d. So if you did z1 squared plus z1 squared plus z1 squared, d times, that would be gamma 1 half 2d, which is not what we want. The funny thing is, when you add up independent gammas, instead of adding up the scale parameter, you add up the shape parameter. It's quite a funny thing. So what's going to happen is that this has the distribution. Well, by the way, it is called chi squared with d degrees of freedom. So I'll even write in words. It comes up so often in statistics, you probably even saw it in first year very frequently, d degrees of freedom. The definition is nothing other than d independent normals squared added together. And you might remember a lot with chi squared n minus 1. That's what happens when you do it from sample means. So we'll get to that later. But for the moment, this is just the theoretical definition. Chi squared d. Now that is exactly the same. The fact is that, okay, so the definition is chi squared d is this thing. The fact is chi squared d is the same thing as gamma. You add up the shape parameters, amazingly. D over 2, comma 2. So why, okay, so that fact follows from a more general fact about gammas. If x is gamma a comma b, I could do it with 1 both times, but let me make it a subscript 1, and y is gamma a subscript 2 d. Okay, and if these are independent, remember that's my symbol for independent, that implies that x plus y, the sum of two independent gammas, they have to have the same scale parameter, have to be on the same scale, has distribution which is gamma, sum of the shape parameters, a1 plus a2, comma, b. So same scale parameter. It's an interesting fact. And you can see how that follows, that then if I have d independent chi-squared 1s, I add up 1 over 1/2, d copies of 1/2 gives me d over 2. So that is why the chi-squared with d degrees of freedom is the sum of d copies of a chi-squared with 1 degree of freedom if they're all independent. Now, I of course haven't yet proved this. The proof, we're just going to wait for the multivariate chapter, because I just thought it's so important to mention it now. But to talk about sums of random variables, that's a general thing that we all talk about in multivariate. So this is just a taster at the moment, and I'll prove that for you later. And then there is another, the final special distribution that comes up a lot in the continuum case is beta. So let's call u, I'm going to use a new letter, it's going to be called beta. Let me call it A1, A2, because I want to match the notation here. It's actually closely related to that. But often people will use alpha, you might see in other works, often it'll be the two parameters will be called alpha, beta. But they have a kind of symmetrical role. And beta is a continuous random variable, but only on the interval 0 to 1. So this is a classic random variable for proportions. Now, as you know, whether I include 0 or 1 or exclude them doesn't matter for continuous. So with density, fu of u is equal to u to the power alpha minus 1, or a1 minus 1, and then 1 minus u to the power a2 minus 1. So there's two parameters. They govern the exponent that you get for u and for 1 minus u. And then there has to be a normalizing factor, which is often called the beta function. I'm just going to imagine that to be a capital Greek beta. It looks exactly the same as a b, of course. So b of a1, a2, where... Now, for the moment, this will be a jumble of formulas. I promise you, once we do the multivariate stuff, this will all come out as a beautiful unified thing. Beta of a1, a2 is related to the gamma function, gamma of a1, gamma of a2 divided by gamma of a1 plus a2. So it turns out that is the appropriate normalizing constant. That's just a constant. So, this happens to be the exact constant needed to make the integral of this equal to 1. Every density has to have integral 1. And that beta function is the constant needed to make it work. And the other amazing fact about that beta function is, well, not the beta function, the beta distribution that's really tied in with the gammas. If for x, y as above, okay, remember x and y independent gammas, then you might be interested in the proportion of the sum that is represented by x. Remember, x is a gamma, y is a gamma, and x plus y is a gamma. They have associated scale parameters a1 and a2. And the question we're asking is what proportion of the total is represented by x? That's the question that B1 answers, that the beta distribution answers. So u, which is defined to be x divided by x plus y, has the distribution which is beta with parameters a1, a2. You'll notice the scale parameter drops out. There's no scale associated with a beta because the scale is common to x and y and to x plus y. So that scale parameter is just divided out. The b doesn't appear anywhere. What does appear is the shape parameter. So beta has two shape parameters, and it is pretty much exactly the distribution of how much of a sum of gammas is represented by just one of those individual gammas. It turns up all the time because it has these nice mathematical properties, and we'll do a bit more of that with multivariate. So I actually want to stop. Let me just double check. I think that's everything I want to say about gamma right now, except so one other gamma that you might remember is that gamma, a special thing happens to the gamma when the shape parameter is 1, because of x to the alpha x to the a minus 1 becomes x to the 0, so it drops out. So if a equals 1, this is just an exponential. Now, can someone remind me, there's two conventions for exponential. Did I call it an exponential lambda or an exponential beta when I talked about it? Maybe exponential lambda? I'm not sure. The relation between them is that lambda is 1 over beta, so, or 1 over b. So gamma with parameter 1 comma b is, I'll just say it this way, exponential. That's the same thing with, well, beta equals, sometimes it's called beta, and sometimes it's lambda, which is 1 over b. So we'll revise, I think I called it lambda. Remember, exponential has lambda e to the minus lambda x, that's the density. So lambda is 1 over b. Sorry about that, that's the real. Yeah, so just that little summary I made. You might remember exponential from before. It's something that has the density lambda e to the minus lambda x. The key fact about that is the e to the minus lambda x. And gamma has density x to the 0 if a equals 1, e to the minus x over b. So b is 1 over lambda. Anyway, there's good reasons for both of those parameters, but you just have to remember whether you're... because exponential lambda is very closely related to Poisson lambda in a way that we'll get to later. But anyway, so all these things are connected. There's a reason we've picked out these distributions, and they're not just random. But for the moment, I'm actually going to rest the field as far as continuous random variables there, because I have two other things I plan to do today. Talk about... Well, I might start on multivariate at the end, but before I do that, I want to talk about one particular thing from even discrete variables that we did some exercise about and just try and unify it a bit. And that's the first step decomposition when you're doing problems. Now, people would have seen this, right? At least in some of the solutions to exercises, solutions to the quiz, which you probably looked at, there's frequently a pattern where instead of... You might have typically it's a game that could take a large number of steps. You don't know how many steps it's going to take. And you want to find the probability that a certain person wins, or the probability that something happens, or also you might want to find the expected time doing something. So all of these are common problems. And we have frequently solved them. The most basic ones you can solve using series. So we're just going to go back to discrete problems for now. Okay. So this is it's a little bit of a general introduction that I'm going to give. Frequently, you have questions of the sort like, probability that, person A wins a certain game. The game is often a repeated number of rounds until something happens, or, probability that you get some pattern. You often might get this pattern in die rolls. Die roll 1 before 6. Okay, so something like that. Some kind of probability. Also, expectations can be done in this way. Number of rolls before first 6. Now, this last one is, of course, that's an expected value of a geometric 1/6. So some of these fall into the examples that we've already done, but some of them don't, and that's the key thing. And some of them can't even work using the existing methods. So let's talk about the methods. The first method is you might say that a problem is a standard variable, for example, geometric or negative binomial. Very infrequent. You don't tend to get Poisson in questions about these games, because games you're waiting until a certain number of things happen, or the first time something happens. So it's not so much to do with Poisson, because Poisson, of course, becomes vanishingly unlikely after a certain point, whereas a game has a bit of a loss of memory property. If you're at a certain point in a game, you tend to keep going as if the game had just started. So it tends to be more in the nature of these ones. But those are limited. They don't answer all these questions. Sometimes you can just do it with a series. Okay, so a series can answer some more complicated questions. For example, A, B, C, D flip coins. and we want the probability that A flips the first head. Okay? Series can often solve this quite easily because it's not exactly a geometric, of course, because although you could, you can relate it to a geometric, but it's not something, one of the standard formulas for a geometric. If it's geometric 1/2, that would be the time till the first head. And then we're looking at the probability that n is, of course, you would write it probably n equals 1 mod 4. That would be the way you say it, because it's 1 or 5 or 9 or 13. So you can write it in terms of a series, albeit not one of the normal series for a geometric. You would do, you know, I equals, let's say I equals 0 to infinity, probability that n equals 4i, right? And then this is going to be sum I equals 0 to infinity. I can write that down explicitly in the geometric 1/2. It's 1 minus p, so 1 minus 1/2 to the power. Why did I say 4i? I meant 4i plus 1. Sorry about that. So that's 1 minus 1/2 to the power 4i. Remember, you do n minus 1 in the superscript, and then times p, which is 1/2. Right? I'm just summing up the probability mass function appropriately. So it is a matter of the first term divided by 1 minus the common factor. The common factor is 1/2 to the power 4, so 1/16. So that would be 8/16 divided by 15/16, so 8/15. So that's an example of how you solve it using series. And I'm doing these methods in increasing order of what works, because sometimes even the series method doesn't work that well. So an example of that is if you kind of have, even if you just had 2 games in a row, right? So in order of kind of, I guess, more of a sledgehammer. So I'll just say in order of what works. If you're lucky, it might just be a very standard thing that you can, you know the expectation of a geometric. Here, it's not a standard thing for a geometric, but you can still do it using a series. Sometimes even just a single series is not going to work. Sometimes you might want to do multiple series, and how do you put those together? You might want to use linearity of expectation. Now, linearity of expectation is a very fancy name for something that's a lot simpler, which is that we already know, we've said many times, expected value of n1 plus n2 is equal to expected value of n1 plus expected value of n2. Okay? Or you can do that for any number. Now, there is no independence requirement, so this is surprisingly useful. And I once used the word indicator function method. That's a special case of this multiple series method. Okay, so no independence required. Why is this useful? Because okay, well, I'll just leave that one as one thing that you can do. Another thing that you can do is law of, you might be finding probabilities or expectations. Mostly the same methods work because of the close relation. And we had from chapter 2 the law of total probability. I'll remind you of what that said. If B1, B2 up to Bn are, the fancy word would be mutually exclusive and exhaustive events. So you're just breaking up the number of ways things can happen. Okay, so that's a fancy way of saying exactly one of the BIs happens. Okay, exactly one of the BIs happens. Then the probability that the target event you're interested in happens given, well, can be broken up according to the probability that B1 happens, probability of event given B1, and then the same for each of the different ways that it could happen. So these are the different ways it could happen, B and probability of given Bn. So we already know that. And probably something that wasn't emphasised as much is the law of total expectation, which actually follows from the law of total probability by... it's because we didn't really talk about conditional expectation a whole lot. We will do more involving conditional expectation, but conditional expectation is just the expectation where you use conditional probabilities instead of normal probabilities. So, so just in case you're wondering what a conditional expectation of a random variable is, let's just focus on discrete random variables. So n given bi. What is the definition of that? You just sum up all the conditional probabilities. Conditional probability that n equals. N equals n given bi. So, law of total expectation. So this is what conditional expectation is. So I'll just say all values of n. Because we're talking about discrete random variables, that's a perfectly good definition of conditional expectation. It's exactly what you'd expect. It's sum of n times the probability. It's just that the probability becomes a conditional probability rather than a non-conditional probability. And it also is exactly what you'd mean in colloquial speech about it. What's the expected, you can have two people flipping coins, and what's the expected number of rolls given A wins versus what's the expected number of rolls given B wins. It's exactly according to this definition. Anyway, so the law of total expectation is exactly the same as the law of total probability in this context. The expected value of n expected value of n overall, unconditional, is equal to the sum of all the conditional expectations times the probability. So, in other words, how many rolls do I expect overall? It'd be the same as the number of rolls I expect given A wins times the probability that A wins. So B1 would be that A wins. Expected value of n given B1 plus ... So you just break it up according to all the different ways that it could happen. Probability that the other guy wins, and the expected value of the number of rolls given that the other guy wins. Okay, so that law of total expectation can be very good because, when it's just coming down to do a single series, it can get too complicated if there's three ways that it could happen. They all get tangled up together. But you could divide it according to the three different ways it could happen: probability times expectation given that happened. And I'll just give you the summation notation of that if you want. I equals 1 to n, probability of bi, expected value of n given bi. And once again, the assumption is that b1 up to bn are mutually exclusive and exhaustive events. So that's the law of total probability and the law of total expectation. They're related. And then finally, so I've been building up to this for some time. All of those can be useful techniques. It's just a matter... And by the way, there seem to be two ways of breaking things up here. One way was multiple series using linearity of expectation, and one was law of total expectation. They seem to be two different ways of breaking up an expectation of n. Now, are they interchangeable then? Would you say? I don't know whether anyone has some experience from the problems on the quiz, for instance, or the or just the thinking about some problems on the tutorials. I'll tell you, they're not interchangeable, and they apply to totally different situations. For expectation of n1 plus n2, that's more like a game where you play, if you're thinking about games and number of rolls, that's more like a game where you do game one, then you do game two, and they might be unrelated games. Or they might be related. It doesn't matter because no independence is required. So even if they're related games, this is still valid because there's no independence going into it. That's only when you're counting all the rolls from the first game plus all the rolls from the second game. Then you just add it using linearity of expectation. This is totally different. This is when you have effectively n different games, one of which happens. And so it's sort of like, they don't have to be n different games. They could be n different cases. So this is like a case bash, breaking things up into different cases and adding up the respective probabilities. So those are complementary. They're not, they don't work in the same situation, but they can help together in different situations to solve the problem. Okay, so that's sort of a summary of techniques that we've examined, and I want a technique that we haven't examined so far, which is the first step analysis. Now, if you've read the notes that were given, this is talked about a few times, and also in the solutions to the tutorials, you should have seen a few that had first step analysis in them. Also in the solutions to the quiz. So what is the key feature? Once again, when you have a game, you have a few states that you could be in. Most basically, if you're having a game where two people alternate, then you have the state where A is winning, and then the state where, or a state where A is about to go, and then the state where B is about to go. So you have, I'm going to try and give a general formulation of this, and it actually matches something that's, goes on in later courses, but I'll give the basics. So you have a number of states, and states, the word by itself doesn't imply that the state includes all the information about the game, but we're going to assume that the state includes all information you need about the game. So there's nothing you might have to ask about the game that's not included in the state, except, and this only applies to a certain number of games, the state does not include the turn number. Okay, so I'll but not the turn number. The turn number is kind of an extrinsic thing. You've just counted how many times you went through. That's important because it's important that there is a finite number of states. So I'm giving the general formulation that works for all first step analysis. Why is it important there's a finite number of states? Well, the finite number of states is when I can guarantee that this will work. And just in practical terms, if you have infinitely many states, it's get very complicated. So this method will work when you can talk about your game in terms of there's just a few positions that you could be in. The fewer the better, because there'll be fewer equations to solve. And then when you have a finite number of states, you have a fixed probability, and I'll even call this Q. Now, should I call the states x and y? Yeah, I'll call the states x and y. I'll keep n for the turn numbers. So qxy of going to state y, given you are at state x. Okay. So that's a fixed probability going to state y, given you're at state x. Why is that the fixedness of that probability important? Well, if the probability is fixed, I can guarantee you'll be able to solve it by this method, modulo solving some linear equations. So, by the way, there are more advanced courses about this, and this actually has a name. This is called a finite state, which is the easiest case, Markov chain. Okay? Now, this is not a course about Markov chains, so you can go to STAT6039 if you want to learn a lot more about that, and then also the STAT3 courses will talk a lot about them. But I'm just saying that, there's a reason there's a general principle that works, because it's a subset of a much larger body of knowledge. But in our case, we're just going to talk, you don't have to know about Markov chains, we'll just talk heuristically about how you solve these things. Then, what you have is the probability, we know everything about the probability of going from one state to another. And I do want to have a sync state. Now, whether it's one or more sync states does not. So a sync state is one at which you just stop and don't continue. At which the game ends. Can you just imagine it? Okay. So, and assume all states are connected to a sync state. Okay? So a sync state is like how someone wins the game. Let's not go into great detail about this. I mean connected ultimately. It doesn't have to be you go straight from that state. I mean via a number of steps. Like, in other words, it has to be possible with positive probability to go on a certain number of steps, and then you get to this sync state at the end. Okay. So if we assume that, and also one connected component. So this will be, okay, so let's not go into great detail. That will be true in all games you talk about. Like, in other words, there's not like one game where you always stay in these states and then totally different states over here. So you can get from any one state to any other state, except you might end up at a sync state. Okay, so you don't have to check these things. This is just describes all the games that we'll be doing. Then you can solve. Okay, there's a few. I'll just say them as facts. You can prove them as theorem. The expected value of the number of turns. Okay, that's the number of turns in the game. I said that n is not a member of the state because otherwise there'd be infinitely many possible states. But the game is such that the turns available at move n don't depend on whether n is 10 or 10,000. You know, once you get back to the same state, you have the same game regardless of how many turns you have. So the expected number of turns in the game is finite. And then the probability, so both the expected number of turns in the game and also expected value of number of turns. Okay, so that's the number of turns at state x, because not all of the turns will be at a particular state. You might be asking how many, for instance, in a rolling game, you might be asking how many turns is Bob in the lead, or is it Bob's turn? That would be a very simple example of that. But that is fine. So I can just guarantee that to you. Effectively, the reason is because there is a geometric tail. All these finite state Markov chains have geometric tails. It's quite easy to prove because there is, because all states are connected to the sync state, there is a positive probability of doing that. If you have a fixed probability of stopping the game, and you have infinitely many chances to do that, that's like effectively bounded by a geometric, because the geometric is first you have a chance to die, and then you have a chance to die, and it's the same chance every time, so that's like a geometric. So it's bounded by a geometric tail. It definitely has finite expectation. So expected value of n, expected value of nx, the probability that you end at state x, or I'm just going to list a whole number of things that you can calculate using the same methodology. Probability that, person I wins. These would be the kind of things that can always be determined. It's effectively where you end the game, or what state you are at when you end the game, can be solved. I'm not going to give you the formula for them, except can be found by solving a system of linear equations. And why do I know they can be solved? Because the system of linear equations is determined by these transition probabilities. That probability, I'll even put the word here, it's called a transition probability because, naturally enough, it's the probability of transitioning from state x to state y. And linear equations, and effectively, all of these are, and I'm just going to do it in a conditional sense. It's not exactly what I normally mean by conditional expectation, but let's talk about expected value of n given x. Denote by that the expected number of turns. Now, it's not just for number of turns. It can also tell you who wins, but it's the same method. Expected number of turns starting from state x. Now, this is quite important because the expected number of turns can be different depending on whether you start with person A or person B, especially if you're talking about ENX, or especially if the rules can be A. It doesn't matter whether the rules are symmetrical between A and B or asymmetrical. It still falls in this thing. Symmetrical will be a bit easier because you'll know it's the same for both of them. So expected number of turns starting from state X. Then the first step analysis is, and it's exactly what you'd expect from those tutorial solutions but this is the general form of the first step analysis. It's exactly saying expected value of n. Now, often the game will say you start at a certain, A rolls first. That would already give you what. So really by en we mean en given A. So this will allow us to do the general case. Expected value of n given x is going to be equal to the sum over all states y. And I just talk about qxy. That is, of course, the probability that the first step, so I'll even label that. That is the probability that the first step goes from x to y. So we're just decomposing across all the possible ways that you could go from the first step. Qxy times the expected value of n given y. But that's not quite all, because it's plus 1. It's plus 1 because that first step itself is the first step. Okay? If we're talking about the expected number of steps, then you get the expected number of steps after the first step plus the first step itself. Now, that wouldn't be... there might be a slight exception to that if x is itself a state you might end at, and then then you wouldn't get an extra step. So you just make sure that this makes sense in context. And by the way, I would just remind you that this is nothing other than the law of total expectation. So it follows from the law of total probability. The expected value of n given x is sum of all probability of going x to y times expected value n given y. And then plus 1, because that's how it relates with the extra step. So for probabilities, let's talk about the win probability in a two-player game. Okay, it's slightly different. For the win probability in a two-player game, I like to do it in terms of the first player wins, because, I'll even call it that the next player wins. Okay, that's kind of the way I like to phrase it, because then your states can be kind of simple. The probability that the next player wins, like as in, we've just seen a certain state, is the sum over the probability. Now, the two-player game is critical because in a two-player game, the fact that this fact actually turns out to be more important than you might think. The fact is, not only, you might even wonder, does the game go on forever? The fact is, it doesn't go on forever. With probability 1, it stops. And in fact, stronger than that, the expected number of turns is finite. So in a two-player game, one of them must win. It can't just go on forever. That means the probability of the player B winning is 1 minus the probability of player A winning. That's a useful fact that you can use in this first step analysis. So it's the sum over all, once again, states y, of probability that the transition probability first, qxy, that's the chance that your first step goes from x to y. And then, because it's a two-player game, you're then, if player A is going and they go from x to y, then it's player B. So I want the chance that player A wins, which is going to be 1 minus the chance that player B wins. So that's why there's a 1 minus here. Next player wins given y. That's the story. So that's all I want to say in generality. In generality, this, of course, these are just linear equations. I haven't told you how to solve it. N equations in n unknowns. Because n is the number of states, right? The n unknowns, depending on whether your expectation... you're either doing this case or you're doing that case. If you're doing this case, your unknowns are e of n given x. There are n choices of x. And you've got n equations, and they all relate those n unknowns. So you expect to have a solution. If you know a little bit about linear algebra, that's not always the case. It's the case so long as the matrix is non-singular. I'll just say one fact is the matrix is, for those of you who know about matrices, the matrix is non-singular because of the sinc states. If you didn't have sinc states, then it might just go on forever. So the sinc states and the fact that everything is connected to a sinc state guarantees that it's a non-singular matrix. Okay. So n equations in n unknown, I'll just say that you can solve. So can solve is all that I'm saying in the generic case. Now I just want to do some. So let's do some examples, because that was all quite theoretical. So examples. So A and B play. Okay. First to get... So it's worth noting that the states are not always to do with the players. It's often best to have the states be nothing to do with the players, and then you can just, it's easy enough to recover the players by counting whether they're an even number or an odd number of turns. So you don't have to include the players in your states. The game is, to solve as efficiently as possible, you want as few states as possible. And while you could break it up into lots of states, if you can do it with fewer states, you have fewer equations to solve, and it's better. So first to roll 6 straight after 1 wins. Okay? So that's a funny game. And it goes into how much information you have to put in your state. Here, your state has to be... I'm just going to do it always in terms of the next wins. Now, ultimately, that will be that player A wins, but the symmetry makes it... the probability that next wins, given that I've just seen a I, is equal to... So, and I don't have to make it I can just mean 1 to 5. Given I've just seen 1 to 5, it doesn't... No, 1 to 5 are not all differently. Given that I've just seen a 6. Let's say given I've just seen a 6. And that means it wasn't a 6 straight after 1, because otherwise you would have won. So probability that next wins given a... so in that case, 2 to 6 are all the same, is equal to 1/6 is the... So the states here, I'm going to make the states 1 and 2 to 6. That's because 2 to 6 are all interchangeable here. I'm minimizing the number of states. Given 2 to 6 is 1/6 probability of next wins given 1. 1/6 is the chance that I get to 1. Oh, sorry. And I have to do, because it's a 2-player game, I do 1 minus the chance next wins given 1, plus 5/6 times 1 minus the chance that next wins given 2 to 6. Now, sometimes you give these other names to make it shorter, but I'm just fitting it in the framework we're used to. So that is... it is 1 to... That happens in general. You get 1 total and then minus 1/6. Let me just call this P2, and let me just call this P1. Because effectively we'll have two equations in P1 and P2. So 1 minus 1/6 P1 minus 5/6 P2. And then similarly, you're going to have P1, which is probability that next wins given 1, is it's going to be 1/6 times the chance. Now here's where it gets slightly different. 1 minus P1, right? This is where you roll a 1. Plus 4/6 times 1 minus P2. Why is it 4/6? That's when you roll a 2 to a 5. It's actually different. If you roll a 6 after a 1, of course you win. And then plus 1/6 times 1, because then that's you win. See that? So you have these equations. So that ultimately, that is equal to 1 minus 1/6 P1 minus 4/6 P2. Okay. Now I'm not going to solve this here. That's a matter of linear algebra. So I'll just say there's these two, and you can solve it. I promise you it's a non-singular matrix. So that's an example. Now if we were to do the expected number of turns for that, you don't get the 1 minus. So the expected, I'll just do expected subscript 2 of the number of turns. Right, that means 2 to 6. Okay, expected value of n given 2 to 6. Okay, that is equal to 1/6 times... Okay, I'll say it's 1 overall, because that's, you always have a turn. 1 plus 1/6 times expected value 1n plus 5/6 expected value 2n. Okay? And then expected value 1n is equal to, once again, it's 1 plus 1/6 expected 1n plus 4/6 expected 2n. Same thing. And then why is there plus 1/6? I'll even write it 1/6 times 0. That's when you win, right? That's after you rolled a 1. That's that you get a 6 immediately after rolling a 1. It's 0 because, remember, the roll on which you get the 6 is already counted. That's 1. That's like, after you've seen a 1, you definitely do the next roll. That's this roll. And then there's three things that could happen, and we do the law of total expectation. It's 1/6 times the expectation given you roll a 1. It's 4/6 times the expectation given you roll a 2 to a 5. It's the same. Whether you roll 2 to 5, it's all the same. And then there's plus 1/6 times the expectation given that you roll a 6 after a 1, which means you've already won, so there's no more turns in that case. So once again, you can solve. It's 2. So you can see, in general, a guarantee you given